Okay, I guess we can go ahead and get started. So today we have the pleasure to have Dr. Tabetha Boyajian here, visiting us from Louisiana State University. Dr. Boyajian received her PhD from Georgia State University, and then then received a Hubble Fellowship and decided to stay in Georgia State for a few more years. After which she moved to Yale for a postdoc for a number of years, and then she moved to a faculty position at LSU. Dr. Boyajian is an expert in stars, and as a byproduct also studies exoplanets. And so she's going to tell us about that work today.
Thank you. So thank you for having me. So this, what you've been staring at and what's been staring back at you for the past couple of minutes is kind of like our logo or theme for this project that I've been working on, and it encompasses like several ideas all in it. So first off, it symbolizes. First of all, we found this very strange star, right, in NASA's Kepler mission. I'll tell you about that. And it symbolizes how this star was actually found. It was found by human eyes, right? And what these people saw is actually shown here in the pupil as these very strange fluctuations in its light curve, its light output over time. And lastly, it symbolizes our call to action, so like actually what we wanted to do so we can learn more about the star and figure out what was going on. And so I'm going to tell a story about that today. And maybe a few of you did your homework and you know a little bit about this introduction and what I'm going to talk about, but still to catch us all up. I was a science, or am a science team member of the Planet Hunters Project, which is part of the citizen science group Zooniverse. So many people know Galaxy Zoo, where you look at pictures of galaxies and you can classify them. And this is just using human minds' great ability for pattern recognition. And so the Planet Hunters Project take this, the same kind of interface and structure, and instead of looking at galaxies, we look for planets, and we did that using data from the NASA Kepler mission. And so what Kepler did, very briefly, it was launched in 2009, and it did like the most boring experiment ever. And it stared at a spot in the sky about as big as your fist held at arm's length. And it did this continuously, staring at 150,000 stars in that one spot, this one right here is all the tiny boxes, for 4 years straight, taking a data point of all those 150,000 stars every 30 minutes. That's all it did. And it measured how bright the stars were. And what it was looking for what astronomers call a transit. So this is when you have a star and a planet going around the star, and its orbit is aligned just right, so the planet comes in front of you and the star, and it blocks out a tiny bit of light as what seemed as like this little kind of U-shaped dip in the light curve here. And so you may be thinking that your background being physics, that okay, well this is clearly a periodic signal and time series data. This should be really, really easy to find, right? Okay, so the NASA team and several other independent teams had searched this huge data set looking for planets, and the main idea, the objective of the mission was to find the occurrence rates of Earth-sized planets around sun-like stars. And when the data sets were being released to the public, my colleague Deborah Fisher said, hey, well, wait a minute, what if computers actually miss something? There is this big what if, and so designed Planet Hunters to search for things that might have been missed. Well, it ends up that our volunteers have identified already dozens and dozens and dozens of planets that got missed. And these results, these discoveries, were able to feed back into the algorithms to search for planets and whether there was leaky holes in the pipeline. Okay, so let me show you, zooming ahead, This is a graph of Planet Hunters discoveries only that are shown in red. So Planet Hunters, they're looking at these data sets, they're identifying ones that are shown in black, the ones that are recovered by the computer algorithms, by the Kepler team, but they're also identifying ones that weren't discovered by the computer algorithms. So down here on the x-axis, we have the orbital period in days, going up here, and you have the planet radius and Jupiter radii over there on the left-hand side. And here we have planet Earth, and here we have Jupiter. All the red points are the ones that Planet Hunters have found that are unique. And this parameter space right here, I think is really cool, right? Like even if they are, pretty big and not Earth-like, hey, they're in just the right spot around their host star where really interesting things can happen. Okay, so here are what our volunteers have been able to find to date. Another thing that they also identified when sifting through this data is you're looking not just at things that you're looking for or want to look for. You're looking at every single thing that stars do. And stars do a lot of different things. And our volunteers don't really have the scientific background, but when you're looking at all this stuff, you start to recognize things. So eclipsing binaries, or stars with flares, or CVs, or any other pulsations, or stuff like that stars do. But they came across this one star that didn't really fit into any category, and they started talking about it. So this is the light curve for KIC 8462852. And here we have, on the bottom axis, we have time, and over here we have the amount of light that the telescope received from the star. And in May of 2009, this star went through a transit. And our users noted that this transit looked like what a planet would make, meaning it was as deep, about 0.5%, that a planet would make going around a star, but they're saying it was giant. So instead of a regular transit of a planet going across a star, they had, being several hours, this one lasted for about a week. That's giant. Also what they were saying is that it didn't really seem symmetric. Like remember when I showed the cartoon of the planet transiting around the star and you would have this clean U-shaped dip? Well, this also doesn't seem to be the case for this transit, as a strange slope over here on the left-hand side. So our users were discussing this online and waiting for more and more data to come out, but nothing really spectacular happened until March of 2011. Okay, and then this is what they see. So this is almost 2 years later, right? Where again you have time down here and brightness right here, but instead of just 0.5% drop in the star's brightness, we now have a 15% drop. And again, the shape of this curve is also very asymmetric. So you have it kind of gradually fading off for about 5 days or so, and then it snaps back up to normal brightness, and then pretty much nothing happens after that. Again, for a really long time. So this shows the full Kepler light curve here, so the full 4 years of the Kepler mission. And zooming into the very, very end of it, this is when our volunteers, our users that were going through this data on their own free time, mind you, right? This is when they started really freaking out. Like, what's going on with this star? Nothing about it is normal at all. It can't fit into any of the categories that we know of. As they reached out to the science team, which is where I became aware of it. So what we see here, again, this is time in days. This is showing about 100 days or a few months of the Kepler mission, and over here is brightness, and we see very, very structured, complex variations in the star's brightness, this time dropping in brightness at one point by over 20%. We also see that some of these dips that are showing have different characteristics. Some are very sharp and some are broad. There's ups and downs within the dips, almost like there are a couple of events that were superimposed on top of each other, right? So they freaked out. They came to me, being on the science team. They said, "What is this?" And I said, "That's bad data. We don't want to see that." And it's not a planet anyway. We're planet hunters, right? But our users insisted that they had done some preliminary checks. The data looked good. And so we spent some time looking at it, and everything from what I could tell, the data was good. sent it up to a few folks at NASA. Everything from what they could tell, the data was good. And so we decided to invest some time to follow up on this star and figure out what was going on. And the cool thing about Planet Hunters is that the volunteers that help us with these discoveries, they all get co-authorship, and they get to kind of experience how science works, with these processes, not just in the discovery, but the analysis and things like that. Okay, so the first thing that you do when you're presented with a problem is you want to kind of look, do a little research on the background of what kind of star this is, right? So we can try and start formulating ideas on it. So this is what astronomers call an HR diagram, or a cartoon of one, where you have surface temperature or color down here on the bottom. Hot is over here, cold is over here, where astronomers like to do things backwards sometimes. Here is the star's brightness over on this end, where you have faint and you have bright. The main sequence right here, this is where stars exist for most of their life, burning hydrogen into helium happily. This is where our sun is. It's a main sequence star. From all the observations that we were able to take of KIC 8462852, we're able to tell that it is also on the main sequence, meaning that it's happily burning hydrogen to helium. It lived for about 1 billion years or so, and it was a single star. It didn't really have anything nearby it. It has possibly a dwarf companion that's maybe 1,000 AU away, but it was extremely normal in the grand scheme of things. So this is only 50% bigger than our sun, maybe 5 times brighter, and 50% more massive. Okay, so nothing that really pointed to this star is a little unusual. It was, this star is really typical. There shouldn't be anything unique about the light curve itself. Okay, so if we weren't getting any clues from this, maybe we can kind of get an idea of what kind of something you could have and where would you put the something around the star to get these kind of features in the light curve, since these follow-up observations weren't giving us anything. And so we can make a chart like this. So say you have some kind of clump of somethings in a circular orbit. Okay, and this is confusing, but I'm going to walk you through it first. Okay, so what we have here is we have the orbital semi-major axis. So this is in a log scale, 0.1 up to 100, or a little over 100 AU. And here you have the clump radius. So this is the size of whatever object that you have in a circular orbit around the star. And this is measured in solar radii units. And so the first constraint we can put on, say we're using that 20% dip that we saw in the very last part of the Kepler data. This was the most extreme, and so here you have, can you see that? Let me flash it. Can you see that? It is better seen. Okay, for me, I can't really see it that well. Okay, so for a 20% dip, right, we can put on these constraints. So here you have some sort of opaque clump, and so this is kind of a lower limit of whatever it is. If it's semi-opaque, then this limit would be much higher, of course. Here you have a drop of 20%, 2%, and 0.2%. So you can limit the radius of whatever the something is just based on the depth of the dip itself. Next, we can put a limit based on the entire light curve that we're looking at and nothing looking alike, right? So planet transits, it's very periodic. You see the same thing occurring each time the planet goes in front of the star. But in this case, we see, a dozen or so events in the star's light curve, and nothing looks like each other. And so we can conclude here that, okay, well, the period of whatever clumpy things has to be greater than about 1,500 days. Of course, these things can be relaxed or go away if you have some kind of dynamics within maybe a clump of some things that changes its structure or shape or even geometry orientation. But just for starters, let's go with this. Next, we can put constraints on the duration of the dips. We saw this 20% dip, and it lasted for 3 days. If you have something in an orbit around a star, it lasts for 3 days, that is dependent on its size and its semi-major axis from the star itself. So basically, you cannot get a 20% dip from any sort of material surrounding a star if it's further out than about 8 AU or so. Yes, about 8 AU or so. So you can't get that, and so you can wipe out all of that parameter space there just by the duration of the disk itself. Lastly, we have what's called the light curve gradient. And so this kind of ties in with the fact that you have a, if you have, in the perfect case scenario, if you have a star and the knife edge scenario where you have an object that can create the steepest gradient going in a circular orbit, around the star, that would be a knife edge kind of cutting across it, right? So at a circular velocity at a given semi-major axis, we have a gradient of about 0.5% per day, and this gives us the a limit, outer limit of about 12 AU here. And so with all these constraints here, we've pretty much blocked out all the parameter space except for things between 3 and 10 AU and something a bit stellar size. So kind of big, pretty far out, kind of where Jupiter's would be, something like that. Okay, but this makes a lot of assumptions, and one, but it gives us a place to start. And so if you think of several scenarios, so most of the times when people see curves like this, they think of these class of stars called dippers. So these are typically very young stars that are still surrounded by the material that they were made from. They haven't blown it away. And this is an informative disk. And so imagine this disk was maybe pretty clumpy, and these clumps are moving in and out of sight and blocking out the light in very strange ways. Another idea is that, well, maybe there's an asteroid belt. We have one around our sun, which is a, typical main sequence gig-a-year star. So perhaps this is something that could also be blocking out the light. Likewise, we also have in our solar system, and there's been a few more that's been found out in our galaxy, is that what if you have not just Saturn, but like a super Saturn, some planet with really, really giant ring systems, like on steroids, and this is what's getting in front of the way and blocking out the light. And lastly, there's this whole idea of, maybe the star had already formed planets, and there was some catastrophic collision between two very large objects, and basically annihilating one of the objects and creating a whole bunch of material that's now swarming around the star. And this is what we're seeing. Okay, so with all of these scenarios, they seemed somewhat, to be able to explain some of the data, but not all of it. And the most important critical part of this was that we were not seeing any glow of material that surrounded our star, which you would expect if you had dust going around it. So to give you a little bit more detail, this is what we call a spectral energy distribution. So in the perfect case, you would have a star's light. This is brightness over here, and wavelength. You would have the distribution of light looking something like that. But if you put stuff around the star, so like a continuous disk like this, your star in the center here will emit light, and then this stuff that's around it would absorb the light and re-radiate it in the infrared. And so instead you would get, instead of this spectral energy distribution here, you would have what we call an infrared excess. And depending on the shape or distribution of whatever that material is around your star, if you had a gap in it or something like that, you would have excesses at, that had different shapes or different peaks out there in the infrared. Okay, we did not see this at all with our star. It is completely normal in the infrared, and this indicates that, hey, there's no stuff there. Well, what if we put it in a special configuration, right? These clumps, what if they weren't always like this? And so an analogy to our solar system would be a comet. Okay, so here you have something in a very elliptical orbit. Well, here's our sun, and here would be an orbit of a giant planet right here. but this solid curve right here would be an orbit of a comet. And so the key takeaway here is that whenever this comet body is getting close to the sun or its host star, it would start to heat up and outgas and get really big and be able to block a lot of light. But it spends most of its time out here. And so when we're looking at it in the infrared, it was probably out here where it was really, really cold and we just weren't able to see it. Okay, so this was the idea here. And if you do that same plot that I had on the earlier slide, if you did that for eccentric orbits, right? Here you have a lot of things that are really relaxed. And where's the perimeter space plot? Okay, so here you have, this is the same as we had before, but here you have the eccentric orbits where your velocity is increased quite a bit. And these limits on your 3-day orbit are much, much further out than they were before. You have pretty much the same limit on the depth. You need to get a 20% blockage from an opaque cloud. You would need quite a bit of material in your way. And here you have, where'd he go? I see it. Here you have your light curve gradient constraint over here. And this is a limit on your clump radius is equal to your pericenter distance. So this is just like, practically speaking, you don't want your clump interacting with the pericenter of your orbit. And so this gives us a much larger range in parameter space here that we're talking about. And this little arrow with the IR here, this is your infrared excess that was imposed for circular orbits to be around this point, but if you have something in elliptical orbit, it actually doesn't really exist anymore. So you have a lot of parameter space that you can work with here, but basically it's still something that is very, very large. Okay, so our idea of the best explanation that we have is there was some sort of breakup of a larger cometary body in the system, and things started swinging down into the inner parts of the solar system and fragmenting, and we're seeing this kind of swarm, a family, as you will, of comets that were coming in front of the star and breaking it up. And it was noted several times that this is kind of like, really, comets? Can you really make comets do that? Maybe. But this was the best idea that we had. Otherwise, we had nothing. We had a lot of ideas. And so it came that time where it was like, okay, well, we've got to publish this, and so that's what we did. We wrote this paper, and this title right here, this was carefully chosen. There was like 10 emails that went back and forth about this title. So we called it the WTF star. For where's the flux, and flux, it's synonymous for brightness here. And when there's a question in your title, it's kind of like, there's a very hard paper to write as a postdoc. Postdocs in here, papers are not easy to write, especially when you have a paper of a non-result, as this one. But it was really cool actually, because this paper got some press. And this is an article about, I had some fun with this one, right? Because we have comets in our solar system. They go by and swing around our sun, they leave stuff in the way, right? And Earth goes by and we get meteor showers. So I had fun with this. I was like, these are like mega comets, right? That are coming in whatever solar system they're in, coming around the star. They're going to leave a lot of stuff there. What if there's a planet there and they go through that trail? You're going to have really spectacular meteor showers around this planet. That's what that was about. That was fun. Thought it was over with until this article right here went out, which reported on a proposal that we wrote to observe the star using SETI. So the proposal was actually denied time. We got to do it in the end. But we had really exhausted pretty much all ideas that we had, and it was like, okay, well, we would learn something, be able to rule something else out. And this is my colleague, Jason Wright, was working on this thing where this paper using Kepler data saying, hey, we found all these really interesting stars and systems that we would have never known about if it wasn't for Kepler's extreme precision. And they're weird for this, this, and this, and this reason. But we have a physical explanation for each one of those, right? So what about this one? We don't have anything really explaining this one, so it would be an interesting target to pursue with SETI. So that part of it is an entirely different talk. So I'm just going to kind of leave it at that. But when this came out, I was actually on Mount Wilson during observing run, and I was coming, there's no cell service up there, and I was coming down the mountain, and I finally got cell service. My phone started buzzing and beeping and buzzing and beeping, and by the time it stopped buzzing and beeping, I was at the airport, which is like a 45-minute drive at least, and my phone was dead because it was buzzing and beeping the entire time, and that's because of this article right here. It was absolutely nuts and insane. Very overwhelming. Anyway, there was some sensationalist drama that came over that, but some really good things came out of it. I can reflect now, looking back, that some really good things came out of it. Madness brings cool stuff. So, first thing is, this is like what I tell my Astronomy 101 students, right? This is the infrared flux. This is the thing that really killed all of the ideas that we had, is that we couldn't get any material around the star because it had no glowing infrared. So what if our measurements were bad? Okay, scientific method teaches that, we should be able to reproduce these results. Or maybe even this infrared flux was time variable, right? So maybe it's kind of growing with time as you have particles going around the star, they're continuously grinding and pulverizing with each other, getting smaller and smaller. And it's not until they get into a certain size where they're effective at absorbing the light and re-radiating the infrared. And so the follow-up happened, and no infrared excess was found. Another follow-up happened, no infrared excess was found. Another follow-up happened, and no infrared excess was found, basically saying that, there is basically nothing around the star out to a very, very far radius. Yes. So that was good. Our measurements were not bad. All right. Another study came out, and this was really neat. I was actually at Rochester visiting Alice Cole, and she said, "I have a grad student who's working on these cute little comet models. You should try this." And I was like, "That's hard." Anyway, so they did that, and they turned it around in like a month. It was really amazing, quite impressive. And they looked at this past, the last 60 days of the light curve, and they had these comet models, and they said, okay, well, we're going to throw a bunch of comets at this and see how many it takes to block out the light and match the light curve. And what she found was that there was have to be several hundred giant comets to go around the star around this 60-day period just to get what we see here. Also, what they found is that big one in 2011 that was kind of single and asymmetric, nothing can reproduce that. They tried and tried and tried, but a comet actually makes something that's a bit opposite to that profile. But this was a start.
How big is a giant comet? How big is a giant comet?
In kilometers, I'm spacing on that.
Oh, no, okay.
Back to
In
you.
terms of what they used, actually.
Hmm?
In terms of what they used, if you had a number. If not,
I know, I know.
okay.
I'll get back to you. Okay, what I did not expect was, I was really hoping for like a breakthrough, right? When kind of put this out there, and we say, this is, two things can happen when you say, I don't know. It's like one person can say, oh, well, of course it's this, and another person says, well, look, I'm able to, pull this out. So this happened, which was completely unexpected. This work right here from Brad Schaefer in 2016, he used the Harvard plate stack. So this is archival glass plates, go back to 1890, and they covered the region for this star all the way up until 1989. And what this graph is showing is the brightness measurement for our star in blue And then these are comparison stars that are here in gray. And what it's showing is that over this 100-year period, the star started out 20% brighter than it was in 1989. Stars don't do that, right? Like how can you get, how can you already start with something that's seemingly impossible, right? And then add something else that's really impossible, right? It really threw a wrench in the whole comet scenario, because that means instead of hundreds of giant comets, we're talking about, hundreds of thousands of giant comets, perfectly orchestrated to fall in front of the star, right, continuously over this time period. Well, that was, one, it was frustrating, but also it's really neat, right? That's science. Eventually, we'll be able to make sense of it all. And then this study came out right here, which uses the Kepler data, but a different form of Kepler data. They call the full frame images. So these were calibration frames that were taken every 3 months, and they're able to measure the brightness of this star over the 4-year period that Kepler observed it. So like preserving the long-term variability. Kepler is designed to find planets. Planet hunters don't care about long-term variability. And so that's the data that I was using originally, which is seen here in the gray. Here you see that one big dip in the middle and that kind of cluster of dips there. What they found was that the star ended up not staying constant brightness during the 4 years Kepler observed it. It had this slope of about 1% per year the first 2 years, and then for about 6 months it dropped 2.5%. And then maybe it kind of leveled out about over here, maybe it continued to go down a little bit. That's a little bit unclear, but that's weird. And this is how weird it is. They were able to do some really neat statistics with it, so it wasn't on archival glass plates. First they looked at other similar stars. They're saying, okay, well, we make this claim that stars don't do this. What if it's just an intrinsic variability of F stars, as the star is, that would make them fade over time? And so they looked at a whole bunch of stars that were very similar to it and a whole bunch of stars in the chip. So maybe there was some sort of instrumental artifact or something like that that would make the brightness fade in this way. And so here we have your flux variation. 0 is in the center. You have some distribution of similar stars and stars at a similar location. Here is KIC 8462852 during this first chunk right here. Here is KIC 8462852 during the whole period. So it is very, very, very significant. No other stars do this. Okay, so after this, we're able to get some really cool data, because up until now, we just have, Kepler was an amazing instrument, but it was really boring in a stellar astrophysics sense that it only observed in one color, right? There was just one filter on it, very broad reddish filter, right? We wanted to know if this stuff going across it, it should be imprinting different depths of these dimmings depending on what wavelength that you're looking at. And this will tell us what kind of stuff is moving, material is moving in front of the star. And so just this past year, we were able to observe it. This is blue all the way to red, and this is kind of zoom in the red. And we found that indeed, one, the star continued to dim today, because the plots that I showed you before here, that ended in 1989. This is 2009 to 2013. So this is late 2016 to 2017. The dim continued today, and that there is a color dependence on this, but not as strong as you would suspect if it were normal ISM stuff, about an RV about 3.1. So this kind of favors a larger RV. So the larger particles here at work in this long-term dimming that we see. Another result that came out along these same lines, but still quite relevant, is the GALAX data actually is time resolved in a couple of different ways. And they actually did these chance pointings of this star at this point in time and at this point in time. The gray is the Montet and Simon curve that I showed a couple slides ago. And this is in R, so the Kepler was in the red region, GALAX is in the near UV, and you see that there is a bit of change in how much the star dimmed depending on wavelength, this also led to the same conclusion that whatever this is leads to an RV of about 5. Okay, so we're kind of building up more and more evidence here, and then here we have another paper that came out just recently reporting on both ASAS photometry that goes back 12 years and assassin photometry that goes back about a year and a half, and that's shown in blue. The ASAS data is shown in black here, and the Kepler data from the full frame images from the Montet and Simon is shown in red here. So there is quite a bit of scatter in this ASAS data, but you can see definitely a couple of things. One is that it seems to match up with what Kepler has observed. It also seems to match up with what the assassin data, or what the assassin results also observe, that there is fading through these time periods. But it also shows something that we've never seen before. Another something is that there's got to be some periods of brightening, because look, this doesn't connect up here like this. And it looks like, you know, there is some kind of going up at that point. Don't have a better view at this point, but this is something that we never had before. So this is really amazing, right? But still, what does it all mean? Well, this is kind of, you know, just to sum it up, here we are, this is 2 years after the discovery of, the announcement of the star, and we have collected all this really, really amazing data to try and piece together a story on it. You know, most importantly, so the star has these dips that we see right here. This is the Kepler data, 4 years of data, ultra precise, very strange, nothing really looks alike. And we've seen that this star also dims on very long time scales. We're talking months to years to decades to centuries. Okay, but what we really, really, really wanted to find out is we wanted to get kind of real-time measurements of the star when it was doing one of these things. So we can trigger observations and get high-resolution spectra, get all sorts of follow-up observations so we could really study the kind of material that was passing in front of it. Okay, problem is, looking at this right here, you don't know when that's going to happen at all, right? And you want to be able to, you know, monitor this pretty much in real time, 24 hours a day, and be able to call on help when you need it. And so what we decided to do is kind of bring this full circle. This star was discovered by citizen scientists, and so we decided to continue on this theme of citizen science. And we asked for supporters to buy into this global telescope network with us, and so we could monitor the star continuously. So this was to work with the Las Cumbres Observatory and their global telescope network, and these are all just robots, or robotic telescopes that are stationed all around the world, 0.4 meter telescopes. And basically it's all just Q observing, and it's the only observatory that really is designed for time domain astronomy like this here. And so we were able to, with the help of over 1,700 people, raise over $100,000 to study this star more. And so that's what we did. And for quite a while, we just waited and watched and waited, and this is what we had. And then last May, we caught a break, and this is a copy of the blog post right here that, you know, we shared with our supporters. Is that, you know, here is our brightness right here, and then we see it starting to drop. And that's where, again, everything went completely nuts, but we kind of knew how to handle it, kind of. We're actually very fortunate about the timing of this. First of all, the star decided to do this right after classes had ended, so it decided to wait for that. And it also started to do this at a time when we're all kind of talking together. We're discussing some other results, and so it wasn't just kind of an out of the blue like, hey, it's time to press the red button now. So here we are, and this is actually what came in that next 12 hours or so. and a lot more came after this. There was just a whole bunch of photometry at all different wavelengths, cadences, spectroscopy, we had polarimetry, we had radio observations, we had pretty much the whole 9 yards to just like look and study this star more when it was going through this really exciting state. This is kind of like, you know, whatever is going in front of the star is in between us, and that we can use that to probe what's going on. So the community, and all this basically came from us shouting on Twitter, because that's what people do these days. Funny enough, anyway. Yes, it was very overwhelming to have this community response here. And this was May right here. And this is our continued photometry at the Las Cumbres Observatory. And just to show you what happened all the way through December when the star went kind of behind the sun and we couldn't observe it anymore, we didn't just have one dip, right? We had several dips that came. They're all under the order of a couple percent, right? So we have LC, and then we have Celeste, and we have this kind of depression right here, Scarbray, Encore, and then, ooh, whatever that is. Okay, so these things have names, and I kind of stole that from the people who find asteroids, and they named them because, you know, their catalog names are really boring. So we had this Kickstarter project. It's kind of a way to, like, you know, involve people more into the science. And so the names were nominated and then voted on. And so that's how these names came about. LC is kind of like a shout out to Las Cumbres, LC, right? Okay, so that's kind of a shout out to Las Cumbres, who allowed this project to happen. And Celeste is kind of a play on LC, but kind of flipped around, because at the time we had observed Celeste. It seemed like it was kind of, LC drops really quickly and then kind of slowly comes back up. Celeste looked like it was going slow and then rising up really quickly. And so LC, if you flip it around, that's CL, so Celeste, sky. Okay, so that's how that came about. And Scarbray and Encore are pretty neat ideas. They come along the theme of ancient, like, lost cities. And so the idea here is that something really interesting happened, you know, about 1,000 years ago. So, and the star happens to be about 1,000 light years away. And we don't know what it is. It was probably pretty big, and we're trying to study it more. We're trying to figure out what happened. And so that's the connection with the ancient cities, is that we don't know what happened to those ancient cities, but, you know, we're trying to study it and learn more about it. And this whole business here with whatever that is, that was, you know, at first when we started to see it go up, we're like, oh, well, you know, we do know the star has very long-term variation, right? So maybe we just got the background level a bit wrong, which is very true. We completely ignored that. But then it went back down again. And my colleague Arlo Lando suggested this, that this region right here kind of looks like the Angkor Temple, which is Wat, right? Which is kind of funny because Wat also sounds like what. Anyway, I thought that was really cute. He's quite brilliant. Anyway, thank you, Arlo. So the question is now, is this the new normal? I don't know. We actually just have a couple of nights of data in the past couple of days to find out what it's doing right now, but I can tell you that over here-ish, it's still right on this dotted line. So we're kind of at normal levels right now. So we're able to, after blogging daily since May, able to finally pull this together for publication, and this is the amount of the number of people who contributed to this in many, many, many different ways. There is a lot of AAVSO, so the American Association for Variable Star Observers, a lot of their contributions for the past, like, 2.5 years when the star wasn't doing anything, because that also told us something, right? But, like, we know now when the star did something, but it's really important to figure out what's going on when the star didn't do something. That's also an important piece of information. And a lot of these amateurs were contributing to this in that way. So people were helping any way they could. And we have over 200 authors right here, which is fun managing. Anyway, so main results. I think First, that even though we were very, very, very confident that this was not an artifact in the Kepler data, we're now able to say that it was observed with at least all these telescopes, if not more. And so, and this is all independently using their own pipelines and all that business on comparison stars. We all observed the same thing, so it's not an artifact with the Kepler telescope. Another thing that came out of this is that there's no real clear pattern. The only thing that we saw that maybe resembled what we saw with the Kepler Space Telescope is Scarbray here. So Scarbray is shown with color points, and this kind of solid black line right here that's not a model, that is the Kepler data. Remember, it's ultra precision space data. Okay, and this is nothing shifted or anything like that, and we can kind of see some similarities, right? You have like this kind of like triple peak right here, but this center one is very, very sharp. This window right here actually fell inside of a longitude gap, or you didn't have coverage at the time. Here, you can see right here. But maybe it looks the same, but that's really the only thing that we can pull out of it on any clear patterns. We got a lot of really great spectroscopy of the star during these events. We also have spectroscopy of the star not during the events. If you look at the spectra, during the event minus prior to the event, it is flat. And it's flat in all the interesting lines you could possibly think of looking at. And we also see that there's absolutely no radial velocity variation between these events either. So we're talking about, this is an F star, so it is rotationally broadening quite a bit. These are ISM lines. There's no changes in the ISM lines either. And so pretty much it's boring, it's unimpressive, but that's important because it tells us something. Okay, another fun story is that the NEOWISE mission, sorry, they changed their name too much. The NEOWISE mission was doing its survey of the sky looking for asteroids, whatever they do, and they had pointed at our star a week prior. And then with its, scheduled observations, sometimes it has to kind of tweak and toggle to avoid getting too close to the moon. And so it did that right during LC. Isn't that cool? And then it pointed back and did some other things. So we have, data, infrared data from the Space Telescope right before and during LC. And we don't see any infrared excess during this time. Okay. What about the stuff around it in the sky? So we've got some really great polarimetry covering. This shows right here time and polarization. The LC, Celeste, and Star Bray are shown right here, and the data points are shown with connected lines, basically saying that the polarization, so the neighborhood around the star is very normal compared to everything else around it. And so this shows also the polarization with respect to wavelength right here, and using some weakly polarized stars. So there's nothing unusual about the dust distribution around this star either. What the coolest thing was that we now have colors, so different color photometry during these dips. So before I was just showing you the color was observatory coded. Now this is color coded, so we got B, R, and I photometry. And now the symbols have changed to observatory. And we see that the star is more dippy in the blue than it is in the red. That's cool. That's like when we had the long-term dimming results, right? Like we found that, that was the first time we had this color information also. And we can make these measurements, and we see that one is chromatic, and it's pretty consistent with dust. And there's some stars right there, and I'm going to get back to it. So if it's dust, all right, we can use the opacity ratios for all sorts of minerals that are listed here. And here we have the opacity in R and I, and of B and I. Our measurements are the gray bar, and see where it is compatible with our measurements. And so this is basically saying that our whatever is passing in front of the star is consistent with particles on the order of, you know, a couple tenths of a micron or less, give or take. Okay, so again, the dot, dot, dot. It's probably not aliens, and that's a pretty big one. Like we've seen something, we said, yes, this looks like dust, right? There's dust everywhere, we know that, right? We are all stardust, probably not aliens. If it's dust, we have this idea that, you know, we have this, this optically thin signature that we get from these dips, right? And these are very, very small particles. We have this long-term dimming, which is much larger particles, right? So this is probably some kind of, the long-term dimming is probably just a residual of material that's kind of left over in a ring where the smaller particles have been blown out by radiation pressure. This is kind of the picture of it, but this is still, you know, if it is dust. Because this is a big if right now, and this is because, if you remember when I was talking about at the beginning, it can't be dust, right? Like, that was really, really hard. So like, yeah, we started in the beginning, you know, it can't be dust, and now we say it's dust. So it's magical dust, and that's why I'm giving all of that business there. So there's still a whole lot for us to learn. And you know, first and foremost, I've been concentrating all my efforts into the photometric monitoring, and basically, like, we want to get one of those 20%ers and see what's really there, because that will really be able to help us constrain the location of the material that's in front of the star, and in any sort of compositional opacities, anything like that. We really, really, really want a big one. We want to characterize this long-term dimming, so even if it doesn't dip, we'll still be able to characterize the dimming. And we've also have a big lack of UV and infrared, and millimeter measurements would obviously help our studies as well. So there's also some very, very extensive modeling efforts that need to be going on to follow up the star and any ideas that we have saying this magical dust, where can you put it to make it invisible in the infrared. Okay, I wanted to end it on, since the Oscars were last night, I really thought this was a cool statement. The purpose of civilization is to be able to empathize with others. Movies are a machine that generates empathy. It lets you understand a little bit more about different hopes, aspirations, dreams, and fears. Okay, so I've edited this a little bit. I mean, I think movies are really great, but I think as scientists we can actually kind of train it to our field. So the purpose of civilization is to be able to discover with others. Science is a machine that generates discovery. It lets you understand a little bit more about a world via observation, experiment, innovation, and knowledge. And I really hope, I mean, for us all to kind of be, you know, acknowledge this with ourselves and participate and appreciate like what we do and kind of help spread this, you know, be good ambassadors of science. And that's where I'm ending it on here, is that there is, you know, planet hunters, be a planet hunter. Tell your friends to be a planet hunter, find weird stuff like this. We have a blog here, and there's also this very, very, very active group if you want to know more about the star itself. It's on Reddit, and if you're younger than me, you probably know what this is. If you're not, it's just like a discussion forum place. Yeah, so I'm free to take questions now. Thank you. Yes?
So you're using the lack of sort of mid-IR, somewhat longer IR flux as an indicator of not dust. But if the dust is very small, so it's very inefficient to radiate at those wavelengths, and it can suck up individual UV photons and be non-equilibrium needed. So if you look for things like 3.3 micron emission and things like that that are indicators of those sorts of processes.
We don't have a lot of infrared data at this point. We have run, there's my colleague Mark Wyatt wrote a paper last year that goes through very specifics of when you will be able to get the infrared excess depending on the particle sizes and all this business, depending on the dip size as well. And that's one of the motivations we want one of those 20%ers. It's one of the also very strong motivation for us to want JWST to work to look at this because, I mean, the signal to noise, that would provide a lot more constraint on the system as a whole.
But if it does, part of the distributions are all very, kind of very skewed to the small. You get a very high R value from the soft. And it's kind of like the dust that surrounds many deflection networks. You know, it's optically thin, but it doesn't really emit. It's not in thermal equilibrium, so it doesn't really emit at some temperature that you can calculate.
Right, yeah, we have two different flavors of dust that we've detected. We've had the dust from the long-term dimming, which is RV of 5 or so, and then the ones from the dips, which indicate much smaller particles. And so it does become a complicated problem, but still you have, even to get a 2% dip, that's a lot of dust. And you have, what, 7 months of dippings, right? This stuff all does accumulate in the total opacity that's passing in front of the star, depending on where it is and the geometry it is. This is only the stuff that's passing in between us, right? There's, I mean, yeah, nature says there's going to be some above and below us that we're just not seeing at all.
But a few percent of the flux from dust are converted to 3.3 micron emission. Really bright.
So this is one star out of tens of millions that Kepler looked at. So you're looking at something that could be an extremely unusual coincidence. So for instance, could you have two stars that are in orbit perfectly face on, and then have a large planet around it or something else which has a very, very large disk around it? You can go into parameter space here because it's such a rare object. So do you have radio velocities of the F star? I know it's difficult because they are light, but
Yeah, so it's, I think we can limit a companion around Jupiter size out to a couple AU. So there's nothing that's nearby close in. Its spectra is like absolutely boring. And you know, there's a planet of some sort, even around one or both of the stars, as you're mentioning. A planet can't block out 20% of light.
no, but a disk can. So if you look at it, there are occultations of stars through Saturn's disk. So what do those look like? What are the dips in the stars that go through Saturn's rings? Do you know what that is?
Yeah, I know what that is. I don't. What do you mean? What do they look like?
Well, you can, if two stars are like this and they're face on, polar orbits are very, very stable. And so you could have a planet in polar orbit, in a binary star system like this, and the planet could have a very large ring, which could be causing something.
A ring, like, so you have star, planet.
I'll talk to you later.
Okay. But we still only have, it's a single star.
How do you know?
From radio velocities and high resolution imaging.
What if the orientation is directly toward you, so they're actually spinning like this in the line in the sky?
Then we have high resolution imaging, which rules out anything delta magnitude of like 5, 8. I can't recall at the top of my head or so, down to like 40 AU. And then there's no presence of another star in the spectrum. Just not radio velocities, just the overall spectral energy distribution. You would assume that another star would be imprinted there as well.
Yeah, 2 F stars.
2 F stars.
2 F stars going like this with a polar ring like this. So you haven't ruled that out, it sounds like.
If they were closer than 40 AU, then no, we haven't. I think you could probably get 2 F stars there, but then I think the luminosity would be a little bit wonky.
You have really good distance then to this.
We've got a fair enough distance. We have, because we did a spectroscopic parallax. And so that puts us about 400 parsecs. So next month, Gaia results are going to come out, and that'll really like came back, the first Gaia data release came back with, I mean, large errors, so it didn't really constrain much, but they weren't large enough to fit 2 F stars in there. They were just normal large. If that makes sense. You had a question?
Yeah, you talk a lot about LC and a little about Celeste. It looks like Scarborough is really symmetric. Is there anything special to that, or am I just misinterpreting your plot? It looks like it didn't have this kind of sharp fall off on one side and gradual on the other. Is that not correct?
Yeah, so Scarborough has, I mean, it's very interesting because it does have, it lasts for about 3 weeks,
Yeah.
right? But it has that very sharp
Mhm.
kind of feature in the center.
Yeah.
And then, I mean, maybe it's a play
And
on our
also
eyes, but
it's
we
got
can't
two,
really
right?
tell, you know, the Kepler data overlaid it, right? To kind of guide your eyes.
Yeah.
But we don't really know if that's like
Because
what
of the
happened or
gaps
not.
that are
Yeah,
there,
because of gaps. But we
Yeah.
do see that there's no real long-term variability on the timescales of, you know, hours or even less than that, except for during Scarborough. That's the only time where it's changed very rapidly. And so all those points that we show there are daily averages. Yeah.
If it's cost, you expect it to survive, you know, for a long time. It's there all the time, right? It's not something like really like a transient object, you know, that just show up very briefly then dissolve. If that's the case, now you know you expect something like 20% of reflected, some fraction of that to be reflected towards you. It's dust, and there is no evidence for that.
No, so, I mean, yes, there, perhaps you have, there, perhaps Watt, I don't know, like, we don't really have a baseline level yet, right? So, I mean, over a century ago, the star was 20%
This reflected
brighter.
light should be, it should be there all the time. You can detect that anytime without, transit.
So how would you tell the reflected light apart from the,
But you didn't say it. You'd be able to see that, from polarimetry.
oh, okay, yes. I thought you were talking about around the star.
Yeah.
So, yeah, so the polarimetry shows nothing unique, both in and out of dips.
So it guess to me it's more like a really a transient object. Just shows up, then it's gone.
Yes, but it has reappeared after the Kepler spacecraft observed it. That was one of the things that we had to accept early on, is that, hey, this may be a transient object. Maybe it's just something, you have and then you have the star. Maybe it's just something just kind of like passing by in space. And like the geometry, like it's really hard for my head to wrap myself around something like that. But the fact that we're seeing it again in 2017 kind of indicates that, it is kind of bound to the star itself and not just passing through interstellar space. Maybe you have some kind of ripples in the ISM that are being really weird. Or some kind of junky disk around a quiescent black hole or something like that, that's somehow producing these strange observations. So yes, I mean, it is a transit aspect that we don't know when it's going to do its thing again, but it looks like it does repeat somehow. That makes sense. Okay, we should talk more about this.
Okay, let's thank Tabetha here.